So everyone, welcome again to our iTelescope webinar. It's Friday. It's wonderful Friday, isn't it exciting? And we're going to go deep into science. It's going to get a very hot topic. It's about watching a red supergiant explode. Very exciting. We haven't done this at all. So I would like to welcome Wynn Jacobson-Galan, who is an NSF, so National Science Foundation graduate fellow, research fellow at UC Berkeley. So we're going all the way to California. I've been at UC Berkeley, by the way. That's where I saw Stephen Hawking live. It was fantastic when I was a student. It was a very big moment for you. So let's see, Wynn, jump on board and let's see if he's there. There you are. And yeah, just unmute yourself. There you go. Hi, Wynn. How are you? So nice to have you. How's UC
Hi.
Berkeley?
It's great. It's a nice sunny day here. Yeah, I'm really happy to be here and to talking about supergiants and explosions and stars and all that stuff. Yeah.
And all that stuff. Let's get going. We're looking
Yeah.
forward to it. It's all yours, Wynn.
All right. I'll share my screen here.
Yes, we can see it. It's all good.
I'll just minimize the meeting controls. Okay. All right. So yeah, like I said, my name is Wynn Jacobson-Galan. I'm a Ph.D. student, a fourth-year Ph.D. student at UC Berkeley. I've kind of done two places for my PhD. I started at Northwestern, and then my advisor moved out here, so I moved with her. And I'm finishing my PhD out here. And primarily, I work on the evolution of massive stars, supernovae, the explosive deaths of many different types of stars. And today I'm going to be highlighting just one type of very beautiful and fascinating star in the sky, the red supergiant, and how we watched one very, very far away explode in real time. So that all sounds very technical. The first half of my talk will be kind of zooming in and then we'll be zooming out. I want to summarize kind of how do stars live, how do stars die, what are supernovae, why are they exciting, how do we observe them, and getting into some more technical science at the end, which is more related to the discovery that we performed as a team here at UC Berkeley and throughout the world last year. So yeah, like I said, outline, I want to go through the evolution of massive stars so that we're all on the same page. I want to talk about supernovae, both observationally, theoretically, all things like that. And then a very specific kind of story of one type of supernova called 2020 TLF, where we observed both the supernova itself and the star that was responsible for it in a distant galaxy, which was unprecedented at the time. So I kind of want to start the talk very practically and very simply with, what is a star? And to me, even though I work on them, I still think that it's a complex question because stars in the night sky, may look like little points of light, but when we resolve them with telescopes, they're these amazingly complex balls of gas. And then when we model them, we understand that the interiors of stars are extremely complex. There's all sorts of overlapping gases and different elements and fusion happening. And that's all really exciting and amazing. Stars come in different sizes. They come with friends, they come in binaries, and they all have very different fates. And so a simple definition that I keep in mind is just, it's a self-contained sphere. Somehow it's in equilibrium with itself through gravity. And the equilibrium of this star is held about by the fact that it's inside of its core. It's fusing some hot gas, usually it's hydrogen, into another type of hot gas, which for our sun right now, it's hydrogen into helium. And as I showed, there's a lot of different types of stars, and they're depending on the type of star and the mass that it's born with, its ultimate fate or life cycle is very different. So I'm interested in supernovae, so I've highlighted different endpoints here. I'm really excited by the explosive deaths of stars, but how we get there is actually very different depending on where we start. So you can start with very massive stars, blue supergiants, red supergiants, and all the way down to even sun-like stars, white dwarfs, exploding as very different types of supernovae in the night sky that we try to observe with our telescopes. So how do stars support themselves, and how do stars create the elements that we see on Earth? How do stars create elements that exist in our universe? They really are the factories for what we call nucleosynthesis, the creation of elements that we have in our bodies. And it's not only the process of going from the star itself, but the star and its endpoint. So let's start from the beginning. There is an isolated cloud of hydrogen gas. It's floating out in the universe, and at some point it's going to get too big to contain itself, and it will collapse under its own gravity. And the increase in temperature will ignite helium in its core, and that burning will allow this star to be now a star, a self-contained sphere where the internal pull of its own gravity is now supported for the first time by some internal energy source or supply, which is fusion in its core, pushing back and saying, you know, gravity, you can't collapse me anymore. I want to be a self-contained system in the universe. And so that's great. This is what we call the main sequence. That's what our sun is on right now, and will be on for several billions of years. And that's a very long period of stability in a star's life. And so most of the time, for the things that I study, I'm not looking at stars that are typically on the main sequence. I want stars to observe stars that are well off the main sequence and ready to die. But for most of a star's life, the main sequence represents a period of a lot of stability and not a lot of chaos. And so, yeah, burning occurs for several millions of years, so even billions of years in the case of the sun. And for the sun itself, maybe if you want to take one thing away from this talk, is that the sun actually does not have such an explosive fate, as I will discuss, for much bigger stars like red supergiants. The sun itself will not explode, but rather will continue to evolve. It will puff up, it will shed its outer layers, and it will create something even equally as fascinating, which is called a white dwarf star. So it's a very compact Earth-sized star, but it's about the radius of the Earth, but it's the entire mass of the sun basically contained inside of this radius. And it's composed of carbon and oxygen. And as I'll discuss later in this talk, white dwarf stars are actually very capable of exploding. But unfortunately, in the case of the sun, its byproduct will be a white dwarf star, but because there is no companion or friend with the sun, we have no way to make that star explode on its own. So let's go back to a massive star, which we do know explode on relatively quick timescales, so that we can get to the explosive end, the supernova. So we're back at the main sequence. We're going hydrogen to helium. Finally, we get off the main sequence on this massive star. So by massive star, I mean 8, 10, 15, 20, 50 times as large as our sun. So pretty massive. And the intense pressures and temperatures inside these stars allow it to burn and create elements much heavier than just hydrogen to helium. And so we start to burn helium into carbon for several millions of years. And that actually is not the end. We start to burn carbon into neon for only 1,000 years. And I put an asterisk here because this is one simple pathway of elements creation, but there's actually so many beautiful elements that are created as byproducts. This is just like the one generic pathway that we learn in stellar evolution that we generally teach. But in terms of timescales, maybe you've noticed that we've gone from a main sequence that's hydrogen burning to create helium that was several millions of years. And then now we're at a point where the burning only lasts like a few thousand years. So the time scale is dramatically decreasing. And so depending on what's happening inside of the cores of these stars, it's actually signaling the end, or the final stages of this massive star's evolution, which is really fascinating because we should try to understand stars both in their stages of stability for long periods of stable burning, and also in their final moments before they explode, which is something that I'm personally very interested in and represents a very open question in stellar evolution all the way into supernova science. So it kind of bridges the gap. So neon finally is created in the core, and the temperatures continue to rise and dramatically continue to rise. And because of this, we can now start fusing neon atoms to create oxygen, the oxygen that we have in our air, that we breathe here on Earth, synthesized in the cores of massive stars. And this is a process that actually occurs on a relatively human timescale. You can burn and fuse the amount of neon in the core of a massive star in a few years. So think about what you did in the last few years, and that's how long some massive star has taken to take all of its neon, which is in our signs, like you see on neon signs on the side of the road or something like that, and that element pushing those atoms together to create oxygen in a few years. And then in a very dramatic, almost final end of evolution, we have oxygen atoms smashing together in even higher temperature environments in the cores of this massive stars and creating silicon. So the silicon in our computers, the silicon that has a valley named after it here in California, that's a process that happens for, of order a year. So very, very quickly. And it's because really that the process is very dramatic in the amount of energy that's released. So as I said before, the star itself in isolation really wants to collapse inward. Gravity is a vicious force that wants to pull things inward. But fusion, this energy supply inside these massive stars, is a saving grace, and it pushes outward. But unfortunately, in these higher element burning stages, the amount of energy that's released per burning stage starts to be less and less. So how much energy can we really get out to push back against gravity actually turns out to be much less than earlier stages in the massive star's evolution. So that's tricky for the star because it really doesn't have a lot to work with, and it needs to continue to evolve. And unfortunately, its life is, has an end date. And so this really is its last year alive. And as we push forward into its last week, we'll have the final element creation happening in the core. So the silicon atoms inside this massive star's core are now able to smash together to create iron, nickel, cobalt, things like that. So the iron that we have in our blood, this is the exact location where these elements are synthesized, where they're forged in the universe. And this time scale is only of order a week. So the amount of iron that is created in a massive star's core is synthesized within 1 working week. And so this really is our last week alive if we're thinking about a massive star's evolution. And unfortunately, iron is a very stubborn element. Iron does not like to be fused with other iron atoms. And if we are able to fuse it together, the amount of energy that we can get out to try to support our massive star from collapsing in on itself is really insufficient. So we're at this point where the core is no longer a viable option for producing enough energy to save the star from collapsing in on itself. And we have what you might have guessed is core collapse, or the collapse of this massive star. And so this collapse is extremely dramatic. The core itself collapses in itself of order seconds and releases this beautiful supernova explosion. What happens is the core and the star layers start to fall inward. They essentially, we think, bounce off of the very compressed compact object that's formed, whether it be a black hole or a neutron star, and it drives a very turbulent supernova shock wave going outward, and that unbinds the star and blows all these elements that were synthesized inside the star outward, and those elements are now part of this expanding gas that is a supernova explosion. And those elements get to go on into our universe and create planets and stars and humans and Earths and webinar series and everything else that we have out there. So this really is the factory for creating life, even in death. And so we really are the byproducts of supernovae. Supernovae are such powerful, turbulent processes in the universe and capable of creating the elements that we see on Earth. The highest mass elements have really no other factories for synthesization in the universe. So when we have our calcium in our teeth, our iron in our blood, those things, those elements, and us in some way come from these dramatic deaths of massive stars, of compact stars. And I'll talk about the variety of supernova or explosions in the universe that create or populate this periodic table. I get a lot of questions about how is it what's the difference between a dying low mass star, exploding white dwarfs, exploding massive stars. So the green is actually what we just went through, but there you can see that some of these very, very high mass elements, gold, platinum, things like that, come from merging neutron stars, which I haven't talked about. I haven't planned to talk about a lot, but I'm going to touch on a little bit too. But you can see that the explosion of stars is it's a very diverse topic, and it's one that creates so much life and so much elemental diversity in the universe. So how can we summarize what a supernova is? This is maybe one of the buzzwords of the talk. I think about it as the endpoints of massive stars as well as compact stars. It really is this dramatic expansion of stellar gas. It really is just a transition from a star, which we know was this self-contained sphere, into a turbulently expanding gas cloud. It's all the gas that was once in the star, and now it's just been unbound. It's traveling at high velocities out into space, and emits an immense amount of radiation, and the luminosity itself is of order 1 billion times as bright as even our sun is. And they are these factories for nucleosynthesis, which is the element creation, the creation of things, of elements, the building blocks of our universe. And so, like I said, from the periodic table, stellar explosions are actually very diverse. So we talked about the collapse of a massive star. So that's a single star that's capable of exploding on its own in isolation because it's no longer supported. These are stars 8, 10, 15, 20, 100 times as massive as our sun. There's also the merging of 2 white dwarf stars. So like I said earlier about what our sun will become this very fascinating stellar remnant called a white dwarf. And in isolation, white dwarfs won't do very much, but white dwarfs with a friend, with a companion, we know produce what is called a type 1a supernova, where 2 white dwarfs merge and cause this very dramatic thermonuclear event, which is just another variety of supernovae. We are also privileged enough now to know and have seen and observed systems that we know result from the merging of 2 neutron stars. Neutron stars are the product of collapsing massive stars. So if we look at like one slide, one frame above to one frame below, the collapse of a massive star produces supernova, but it will also leave behind this really fascinating object called a neutron star. It's about the size of a small city, but it's about the 2 times the mass of our sun. So it's an extremely dense, highly exotic object. And in isolation, neutron stars don't do very much, similar to white dwarfs. But now we know that neutron stars with a friend, with another neutron star, can merge together to produce what is known as a kilonova and produce gravitational wave radiation. And we've, since 2017, observed those both in gravitational waves and in electromagnetic signatures. And another interesting merging of the two is we could have a white dwarf star eating or gobbling gas from a main sequence star. So like a star like our sun put next to a white dwarf, that star can provide the white dwarf with a means to an end in terms of explosion. So very, very diverse systems here. And supernovae really are, they really have their hands in so much of astronomy. And that's why I really love them so much, is that I, can interact with so many different facets of astronomy, because supernovae are important in many things. So for people that are interested in how elements are created, how we're able to observe different nucleosynthesis or the byproducts of them, how is life created on other planets, things like that. Like supernovae are responsible for the creation of a lot of those heavy elements, so that's extremely important. Stellar evolution maybe is a really direct tie to supernovae because people who study how massive stars evolve throughout their life really need to contemplate how they will die. Cosmology, certain types of supernovae are used to understand how the universe is not only expanding, but accelerating in its expansion. A Nobel Prize in 2011 was the result of this discovery and this connection. And even galaxy evolution. So supernovae, I said and showed that they are this dramatic expulsion of elements and gas into the local environment. Supernovae happen throughout galaxies at some certain rate, and they provide galaxies with the means to create new stars, to create planets, to create life, potentially. And so the way that galaxies evolve is extremely dependent on how supernovae feed back or give feedback to the galaxy itself. So I've been talking a lot about theoretically what is a supernova. We're at a beautiful age where we can observe supernovae in high resolution, high detail in galaxies outside of our own. So what I'm showing here is a zooming in. It's a composite of a bunch of Hubble Space Telescope data. Zooming in on the location, and what we'll see is a supernova going off in a galaxy tens of millions of light years away. So that blip is a time-lapse photo of a supernova going off. So one single star exploding amongst billions of stars in a very, very distant galaxy. And what's so amazing, even if we take less high quality images. So all these were taken, all these images are of different supernovae taken with a telescope just down the road in San Jose. And even with just a 1 meter telescope, we can take science quality images of supernovae in distant galaxies. And maybe what you've noticed is that if we look at these beautiful spiral and elliptical galaxies and things that we see here, the supernovae I have highlighted by the red crosses, you can see that one single explosion just as clearly as the galaxy itself. So what I've always found so beautiful and amazing about supernovae is that the energy released from the explosion of a single star can outshine and is comparable to the cumulative light of billions of stars added together, which is what makes up one galaxy. So if you think about a galaxy as just a collection of stars, all of those stars have their individual luminosity or brightness, and we add all those up and we get the brightness of the galaxy. And then one star decides to explode, and the luminosity, the brightness from that one explosion is brighter, if not comparable to the brightness of billions of stars all combined together. And so that's what I think is kind of evident here by these observations of supernovae. And I've also listed some of the names of the supernova, and just to give you an idea of how the field works. So SN denotes supernova. It's like an acronym for supernova. And then, so for example, 2018 GJX, it's kind of like the telephone number for the supernova at a certain day on a certain time. So that supernova occurred in 2018. So every supernova that we observe in a given year, say 2023, will be denoted by SN 2023. And then we'll just start like adding alphabetical, we'll just keep going in the alphabet throughout the year. So 2023A, B, C, and then we'll go to lowercase a's and we'll go A, B, B, C, C, you know. By the end of the year, we're getting to like 4 letters after the year. So we observe a lot of supernovae every year, and it's only getting better and better, and we're discovering more and more. So I wanted to give a little bit of audience feedback here. So Christian, if you wouldn't mind putting up the first poll. So now you've seen what a supernova looks like in a distant galaxy. And I wanted to see if you all can pick out the explosion in a couple frames now that you all are experts at seeing what supernovae look like in galaxies far from our own. I'll give it a couple, yeah, maybe a minute or so. I don't know. I can't see when it's done, but
yeah, I'll let you know.
Okay.
Give them a minute or so everybody has a chance. And you have a small rest.
Yeah. Absolutely.
Whilst there, you know, whilst the poll's going, let me throw in a very quick question. You beautifully explained sort of the evolution of the heavier elements. Do we know, if you go back in time, what the earliest supernova would have been, you know, in cosmology?
Yeah, so that is a very active field of study right now. And now that we have like even more powerful telescopes like the James Webb Space Telescope, we can look back into the very distant universe to try to look for what we call population 3 stars. So these are the earliest stars that could have exploded. And so these are extremely metal poor, so pretty much just big balls of hydrogen or helium. And they produce you know, these very dramatic explosions. So they should exist. We should find them. We just need a powerful enough telescope to find them. Yeah.
So I've heard that the James Webb has discovered some, or is that still speculation, right? The population 3 is still.
I have not seen anything out, but you know, it's probably like soon to be a press release. Who knows? Okay, so choice 1, 43%, choice 4, 45%. Okay, so we're pretty evenly split here. It was actually choice 1. This is a brilliant supernova from 1994. It's the explosion of a white dwarf star. So I think that the majority, you know, about half of you saw that, but I guess the image is hidden behind the poll for me, but you know, it's hard to know what is like a foreground star, what is a supernova star. So I'm asking you to do actually a harder job than even supernova scientists like myself have to do, because what we have are images of the sky both before and after the supernova. So we can say, okay, here's a distant galaxy. There is no supernova here. And then all of a sudden, boom, there's this bright light. There's this bright source inside the galaxy. So I'm only giving you one data point here. Okay, so let's try another one that might be a little harder. How about this one? This is a really beautiful galaxy, M100, in the southern sky. And I'll say that the supernova that I'm asking you to find is actually one that I worked on. So I've stared at this galaxy quite a bit, and you know, all of us in the field are especially excited when we get to write papers or do work on a supernova that explodes in such a beautiful nearby galaxy, because we get to make
I can
pretty
imagine.
pictures.
I
Yeah.
can imagine. Yeah, by the way, with iTelescope, we've had several, often people, that's what they do as soon as as such a significant supernova is discovered, everybody wants wants a piece.
Yeah, that's great. I think that everyone should be trying to find
Yes.
supernovae, and uh, even in terms of like amateur astronomy or like semi-professional astronomy, the story, I can say the story behind this supernova is that it was actually discovered by an amateur. And then an amateur astronomer with a backyard telescope
Incredible.
was pointing at this galaxy because it was very beautiful and nearby, and they discovered the supernova. Okay, so we have a larger consensus, and I believe that, yeah, that is correct.
I would have thought so. Yeah.
Yeah, choice 4.
Interesting.
But yeah, sometimes if the supernova is a little fainter, then it's kind of hard to detach it from the background of this very bright galaxy. But as you can see, it is one of the brighter sources in the galaxy. And this is supernova 2019 EHK. So I worked on this supernova. It's a peculiar transient. It's called a calcium-rich supernova. So it has a very specific evolution, and its nucleosynthesis is very dominated by calcium emission lines. So that's why we deem it a calcium-rich supernova. Okay, so let's transition into the stars that are the highlight of this talk. So we on Earth are lucky enough to have a red supergiant in our view most of the nights, depending on where you're located in the world. So in the Orion Nebula, we have Betelgeuse. That's our local red supergiant, and red supergiants are these evolved stars that are past the point of burning helium in their cores, and they're extremely large, pretty cool, but puffy, very complex systems. So they're of order 8, 10, 15 times as big as our sun. And they're extremely puffed up. They're 1,000 times as large as our sun. And so you can see actually Betelgeuse in this image on the right here. We have Betelgeuse placed as if it were in our solar system, and its radius goes out to Jupiter's orbit. So these are extremely massive stars, both in mass and in radius. And they are the most common way to produce supernovae in the universe. They live and die very quickly relative to other stars, and they produce one of the most common supernova, which is a type 2 supernova. And a very active field of science right now is understanding what massive stars in general, in particular red supergiants, which I'll highlight in this talk, are doing right before they die. So red supergiants are these, like I said, very puffed up, very evolved stars that are on their way to death. And they're very complex systems. So this is a simulation of a red supergiant's outer envelope. What we have here is a lot of convection, so the turbulent mixing of gases in the outer envelope. This can drive stars to eject material, all a very complex and highly uncertain process. And we also understand through simulations that massive stars can violently eject gas into their local environments. This has been understood through simulations, and now we're trying to observe this behavior and infer this behavior indirectly through both the supernova, the resulting explosion or death of the star, and maybe even observing it before the star dies itself. And yeah, so it is a very much an open question. So we're both on the theoretical and the observational side of this story, of this field of study, and also on both the side of studying just stars alone or supernovae. So people who study supernovae, like myself, are trying to answer this question as well as people who study stars just themselves. And I'll highlight some of the really, really amazing red supergiant research that's happening right on this floor, right here at UC Berkeley. So there's been a lot of simulations done about how convection, how the turbulent mixing inside of red supergiants occurs. So this is one of the most accurate simulations to date by graduate student Andrea Antony, who is looking at convection inside of red supergiants and how it drives potential explosions. So what you're looking at is probably not far off of what is happening inside of a star like, say, Betelgeuse in our night sky. And we're doing it on supercomputers here at Berkeley. And similarly, postdoc Benny Zhang is looking at what happens when red supergiants undergo some sort of eruption or ejection of material. This is like a simulation slice of what we think the star is producing or dramatically expelling, maybe potentially right before explosion. And tying this all together, if this is really behavior that we think is happening in red supergiants, maybe we should be able to indirectly infer this if we observe red supergiants after they die in terms of supernovae. So the true open question, and the question that is the dominant thing that I try to work on, is trying to connect the red supergiants that we see in our night sky, Betelgeuse, things like that, to the explosions that we see in distant galaxies. How do we directly connect the progenitors, the stars responsible for supernovae in distant galaxies, knowing that we have stars in our own local backyard that should be similar in behavior? So it's really about connecting very different scales, very different time scales, very different distance scales. And that's really the main driver of my research. So before I get into the last part of this talk, which is on a little more technical things, but it's on actually what's happening right now in the study of supernova explosions and red supergiants, I wanted to give some definitions before I go on. I think that these will help frame some of the discoveries and results that I'm going to share on a specific supernova. So first, circumstellar material. What do I mean by that? If we break that word down, circumstellar, that means around the star, and material just means gas. So it's gas around the star when it explodes. So if we think about a red supergiant, if it has circumstellar material around it, that means that some of its outer layers were ejected or lost, and now that gas is kind of just sitting around the star before explosion. So think about that as, kind of like shedding a coat when it gets warm, but the coat just hangs out around you. So the other thing is, spectrum. I'll be talking about the spectrum or the spectra of supernovae. The spectra is just breaking up the visible light radiation into different energies, frequencies, or wavelengths. So it's like looking through a prism. And if we take a spectrum of a supernova explosion, what we get to see is the different elements that are synthesized in the explosion. And light curve is something that we use in supernova science to understand how the supernova brightness or luminosity changes as a function of time. Supernovae are not like stars. Their brightness is not constant, relatively constant for long periods of time. Supernovae are transient events. Their radiation is very dramatic in how it changes over time. So in terms of understanding supernovae and the stars that are responsible for it, what we really want to do is understand supernovae by observing them, pointing our telescopes at supernovae as young as possible. So when a massive star is about to die, it may have some circumstellar material around it. It will collapse, the shock wave will break out of the star as it expands, and the supernova, upon starting, will actually slam into material that's sitting around the star at the time of explosion. And that collision will actually induce radiation, induce photons. So if we can actually point our telescopes at a supernova young enough, we can see the star's gas that was shed right before explosion colliding with the resulting supernova explosion. And if we can see that, what we're actually doing is we're probing through stellar death. We're actually probing stellar life. We're seeing remnants of material that the star, while living, ejected or lost before it exploded. And in doing that, we don't actually need to have resolved the star that produced a given supernova to understand what it was made out of, how much material it was ejecting, things like these open questions that we know from simulations exist. We can observe through supernovae at very, very early times. And so to do that, I'm part of a supernova or transient sky survey called the Young Supernova Experiment. We operate the Pan-STARRS 1 and 2 telescopes in Hawaii. Like other transient surveys or other sky surveys, we try to tile or take images of the sky every 3 days. So every 3 days we can see the same patch of the sky. So we can see, was there a supernova there? Was there not a supernova there? And we can try to observe and detect supernovae as young as possible. And that's exactly what came about with this supernova that I'm going to highlight at the end of the talk. Supernova 2020 TLF was a supernova that exploded in a pretty nearby galaxy. I'm highlighting a picture of it on the right. And this is an image taken with the Pan-STARRS telescope and through the Young Supernova Experiment. And as soon as we saw this source detected, we wanted to understand what star produced it, what did the star do before it died, and how can we learn from explosions like this? And this supernova actually yielded so many beautiful observational novelties and that we didn't anticipate just upon detecting it. So I'll go through the story of how we observed and tried to monitor this supernova and why I'm highlighting in this talk when I already said that we observe a lot of supernova a year, so why am I talking about this one in particular? So we detect supernova 20 TLF with the Pan-STARRS telescope. We happen to be, our team happens to be on the Keck Observatory telescopes the same night. And so, we now have a picture of the supernova. We want to now take a spectrum of the supernova to understand what is the type of the supernova, what type of supernova is it? So we observe it with Keck, we take a spectrum, and the resulting spectrum, don't have to worry about why it looks like this or the units or anything like this. But you can think about this as different wavelengths of light spread out over frequency space, and this is the resulting spectrum. And so I'm getting kind of technical in this part of the talk, but the biggest takeaway in terms of the spectrum is that it's an extremely hot explosion, and that these very narrow peaks are actually not derived from the supernova itself, but rather from the circumstellar gas that was sitting around the star right before explosion. So the reason why we see these very interesting features in the spectrum is because the supernova 20 TLF slammed into some gas that was sitting around the star at the time of explosion, and it produces this violent, this dramatic production of photons, of luminous photons. And so we actually caught this supernova so young that we saw this signature of gas that was sitting around the star right before explosion. And so we took this spectrum to our theorists and said, what can we learn from this? And they had models that predicted this signature very well. And it's not really important that you understand why or what's happening with the modeling, but just that we can derive parameters and try to understand the gas sitting around a star before it exploded through theoretical modeling is kind of what I'm showing here. And another fascinating piece of the story is that pan-STARRS, so the telescope that detected 20TLF, actually was looking at the galaxy where the supernova was eventually going to go off for many years actually before explosion. And usually for galaxies that are several hundreds of millions of light years away, we're never going to be able to identify the supernova progenitor, the star that's then going to become the supernova before explosion, because the galaxy is so far away, we'll never see the light from the star individually until now. So what we found for 20TLF is that its star was undergoing such dramatic activity that the pan-STARRS telescope actually picked it up before the explosion went off. And so the way that we did this is that we went back in time and we're looking at images of the location of the supernova zoomed in different filters. And so these are images several thousands of days before the explosion. And eventually the explosion will be there. And so we look at these images and we say, okay, there's no source there yet. And then we look at some images a little closer to the time of explosion, and maybe you can see that some bright source is starting to appear where the supernova should also be, or eventually. And then when we subtract the two, you can see that this really luminous bright source pops out of the images. And maybe it doesn't look that impressive, but actually this is not the supernova itself. This is radiation. These are photons from the red supergiant star itself before it even exploded. So this is the first time that we were ever able to see this at all, and let alone in a galaxy this far away. So the red supergiant that produced 20TLF was so dramatic, so turbulent, undergoing a lot of disruptive behavior in its final year, that it emitted so much radiation, probably through the ejection of material and mass and stuff into its environment, that it emitted so much radiation that we could actually detect it before explosion. And so this is what we call pre-supernova activity. And so in terms of a light curve, just focus on the green points above. The transition here is, this is how we plot luminosity or brightness as a function of time. This is a little technical, but if you want to see what we do in the field, this is how we kind of understand how a supernova evolves. So we plot here what this pre-supernova activity. So this is actually just luminosity from the star. Then the supernova goes off. It's a billion times as bright as our sun. It plateaus and then it starts to fade away. And so what we saw was this dramatic red supergiant, so simulated or visualized here for a press release we did. And then you can see in this changing video, those are individual images before the supernova went off, where you can actually see little flickers of the light produced from a red supergiant right before it exploded. So if we wait, you can see some of the frames are a little bright. There it is. There's some, yep. So there are some individual photons or pixels that are indicating that there's a detection of red supergiant radiation or red supergiant eruptions right before the explosion. And so this is the first time that we saw this. And this is the first time that we knew that this was possible. And then there's the transition from a very turbulent red supergiant into this luminous explosion, which was 20TLF. And we, for the first time, saw this transition from life to death in a red supergiant, which we usually see red supergiants living happily in our galaxy, and then we see supernovae that we think come from red supergiants in distant galaxies, but the merging of the two, the transition between the two, had not yet been seen until now. And so this was a big press release. We were very excited to share it with the world. If you're interested in it, you can kind of look up this supernova. I'm sure that you can find some more specifics about the study. And so what have we really learned from all of this as I conclude this talk? So this specific supernova was the explosion of red supergiant. Given the fact that we detected the star before it exploded, it must mean that red supergiants like this undergo a lot of turbulent behavior, tumultuous behavior right before explosion, so that it's potential that we can detect them even in distant galaxies. So is this a common occurrence? Is this something that was very rare? That's an active field of science right now. That's what we want to figure out. How rare was this instance? And we have to understand from evolution of massive stars, what makes this occur, and then how does it produce the resulting supernovae? So we're really seeing the transition from life to death. And with that, I'll conclude my talk. I really appreciate it.